Welcome again. In this presentation, I will explain the need to model noise processes with something other than white noise. We will consider different noise models, need to model noise. We will conclude with an example. We studied an FIR model which is of the form given here, yn equals bzun plus cn, and then we have autoregressive with exogenous input ARX model which is of the form given here. This is the mixed notation as we discussed earlier. There are also other noise models of interest. For example, here Rmax, which stands for autoregressive moving average with exogenous model. We have an Rmax model which stands for autoregressive moving average with exogenous input model, which is given here, and then Aremax, which is nothing but the white noise is integrated. This is apparently very important for industrial processes, for example in chemical engineering. We have Box-Jenkins model, which is a general model which is of this form G and H, and G and H are arbitrary transfer functions. There is one other nomenclature, output error model, the general form of which is given here, and this is something we studied in the FIR also. G is a transfer function. FIR is an OE model as I mentioned earlier. Others are equation error. The ones that we studied in the previous slide are equation error models. Now we will explain the need for elaborate noise models with an example. So here is the problem statement. Generate data using the following model, and notice that the denominator is not the same, not common, and it is not white noise, it is colored noise. It is a transfer function through which this white noise goes through and affects the plant output. Using this, determine the transfer function parameters, that is, excite the plant with input output signals, excite the plant with input and noise signal, get the output from the data, fit the parameters. So the approach we take is the usual one. We excite the plant with PRBS U and white noise C as before, and then we use the data thus collected for analysis, and using the same method that we used previously, we determine the impulse response coefficients, and this says that there is one sample delay. You can see that at time instant 0 the value is 0. So it starts to have effect from the first sample onwards, so we say that there is one sample delay. That we use in the model that we propose. Of course, at this point we pretend that we do not know the plant model. One sample delay has been incorporated. We use the smallest model for B, only one coefficient. Similarly, only one coefficient for F. We use the smallest model for B and F. Now, when we fit with this, we get the following estimates. The value for B is here. Similarly, the value for F is here, and here is the model that we used. We need to check whether the residual, that is whatever we measured, the plant data that we used minus model estimate, the difference between these two is called the residual. We need to check whether this residual is white. If so, we can stop it. If it is not white, then our assumption is not correct. Whatever we have done is not good enough. Here I have plotted ACF and CCF of the residual. You can see that the ACF, which is the top plot, is not impulse. Remember, if it is white, it would have been a clean impulse function. That is not the case. It is not impulse In fact, it takes a very long time to decay to 0, and hence this is not at all white. So there is a need to model this noise with a more elaborate way. We will have to determine in fact the transfer function h. In this particular case we have taken it as unity. We assumed a very simple model, namely white noise, and we found that it is not at all adequate. Here is the motivation to study noise processes in more detail, which is what we will take up in the next video. Thanks for joining. Goodbye.